Hello friends, welcome to the ATC Double Cut. My name is Micah Woods. In today's episode, I am going to discuss a pretty cool or useful turf hack that I use to make use of soil volumetric water content measurements. Now, those are the measurements that you get from a soil moisture meter like a POGO or a TDR 350. Or a theta probe, the device from Delta T devices in the UK. These types of portable soil moisture meters are used to collect a lot of data, generally in the morning and then again in the afternoon. And I'm going to show how I like to look at the evapotranspiration that has happened from the time of the morning measurements until the time of the afternoon measurements, and from that to get an idea of the water use rates of the grass from any particular area of the golf course. So I'm going to refer to a particular blog post here, and that blog post has a title of Hourly Evapotranspiration, Soil Water Content and Crop Coefficients. I will put a direct link to this blog post in the show notes and in the video description. And I put a couple cool charts in this, or I think they're cool charts. So if you're listening to this, to the podcast version of this episode, I think you may want to check out this particular blog post to see the chart, or switch over to my YouTube channel and catch this on YouTube. So this is something that follows up with the previous post. The previous blog post was one where I showed a turf hack for looking at the soil water content as a percentage just by looking at the depth of the root zone. And if you take the amount of expected precipitation and divide that by the depth of the root zone, you instantly get the change in volumetric water content. So that's pretty cool. I find it easiest to do this in metric, but Bill Kreuzer shared that turf hack that I reshared in the previous ATC Double Cut episode. And as he shared that turf hack, I learned myself how you can do this in inches and in American standard units, United States standard units, because I have been using metric for so long and using the simplicity of being able to get these numbers so easily using the metric system that I had completely forgotten or never even put my mind to thinking about how this could be done in inches. I thought it was an insurmountable problem, and it turns out it's really easy to do. Although I will say it's a bit tricky for me to solve those problems in my head, and I can solve the problems in my head on the go while I'm going around a golf course or other turfgrass site. I can solve it pretty easily when I'm using the metric type of units. So let's get into this and see what I'm talking about, because I want to explain one thing about evapotranspiration first also. Evapotranspiration is the water use of the, or let's see, how should I explain it? Let's say that evapotranspiration is the output of an equation. Okay, it's one of those things that's not reality, but it can be a very close approximation of reality, assuming that your turf is growing in a soil that has water in it. If your turf is growing in a dry soil, then the evapotranspiration rate of the grass will not be what the equation predicts, because the equation output is based on the assumption that the soil has water in it. And so that is one important thing to consider. But let's assume that we have irrigated turf, there is water in the soil. So now our evapotranspiration rate, which is the output of an equation, the Penman-Monteith equation is the standard one to use, then that will tell us given the temperature and the elevation and the day of the year and the humidity and the wind speed and all of these factors, this is how much water is expected to be lost from the grass by the combination of evaporation from the soil surface and transpiration through the leaves. For a turf grass stand that covers the ground, that's almost all going to be transpiration. There's very little evapotranspiration from the ground because the grass covers the ground. So the water loss comes from transpiration. But if you have a Poa annua turf that's mown, let's say at 75 millimeters, 3 inches, okay? Let's say you've got a rough of Poa annua. That may use a completely different amount of water than if you have a Bermuda grass turf mown at 10 millimeters or a little bit less than half an inch. The water use is different because the plants themselves are different. They're different species. They're at different mowing heights, and they respond differently to the weather conditions. So that's where we need to adjust the output of the evapotranspiration equation. The output of that equation is called reference ET, and that is the sign used for that is ET sub O. That's reference evapotranspiration. Reference evapotranspiration is the output of the equation. To adjust to our crop, to adjust to the crop that we are growing, which is going to be some type of turf grass, but it might be turf grass as a tee, as a fairway, as a green, as a rough, and it may also be different species of grass in these different areas. Or it may be a lawn. It may be a Kentucky bluegrass lawn, Poa pratensis lawn at 5 centimeters. It might be a cynodendactylon lawn at 25 millimeters. It might be a Stenotaphyrum secundatum lawn at 10 centimeters. It could be a variety of different situations, and we need to have a crop coefficient for our grass and for the type of surface that we are producing. So the crop coefficient just adjusts the reference evapotranspiration up or down based on the type of crop that we have to adjust the reference evapotranspiration to how much water our crop will actually use. And that's the part that gets a little bit tricky because you don't really have a crop coefficient for your site. You've probably not tried to calculate it. And in the textbooks, it will say that usually we can get by with a pretty good turf grass water use rate approximation for cool season grasses is to use a crop coefficient of 0.8. So that means you take your output of your evapotranspiration equation, which might be 6 millimeters or a quarter of an inch. And if we're using a cool season grass, using the standard crop coefficient for cool season grass, we might multiply that times 0.8. We take 80% of that number, and now we're going to have something that is a little bit less than 6 millimeters. It's going to be 80% of a quarter of an inch. For warm season grasses, the crop coefficient generally is a little bit lower. Usually we'll use a number something like 0.6 or 0.7. And that is the number, these crop coefficients are the percentage of the reference evapotranspiration that we can irrigate with to produce the desired surface. Now I'm going to explain how if you have soil water content measurements, if you are making measurements on a regular basis with a device such as the Pogo or the TDR 350 or the Theta probe, you can go a step beyond just looking at the VWC measurements the volumetric water content of the soil. You can go a step beyond that and start looking at what the water use rate is of your grass expressed as a depth. And if you then compare that water use rate of the grass as a depth, if you compare that to your evapotranspiration, you can then find out what your in-field, real-life, site-specific crop coefficient is, which is, to me, it's really cool. And that is another useful thing that we can do when we start switching between these measurements. I'm going to work through a very simple example from 2 greens on a single day of a golf tournament. On June 9, 2023, I was at Keia Golf Club in Fukuoka, Japan, and this happened to be the final round of a professional golf tournament. The final round of the Landic Challenge 10 tournament was played that day, and it was a partly cloudy morning. I was there from sunrise as the work was getting started, and I went out with my measuring tools as I do. I put a link in this blog post for a short video that describes some of the measurements that I make. Actually, it shows the tools and it shows all the measurements that I make for measuring the performance of the playing performance of a green and also the environmental conditions prior to play. And these usual measurements include the ball roll distance or green speed measured with a stimp meter. I use a Clegg hammer to measure the surface firmness. I use a TDR 350 with 7.6 centimeter depth rods or 3-inch depth rods to measure the soil water content. And I make some environmental conditions. I make some measurements of temperature, humidity, wind speed, dew point, and so on to see under which conditions the grass is growing and under what type of conditions I've just made those measurements. So I take all of those measurements and I also record what time I took those measurements, and that time is going to turn out to be a little bit important here. And then in the blog post, I'm only looking at the water content and the evapotranspiration data, and I'll explain later how I got the evapotranspiration data. So in the blog post, I write, those measurements included volumetric water content, VWC, of the 4th and 11th greens. I took 9 measurements across each green and consider the mean value as that green's VWC. So I take 9 measurements starting in the back left corner, going over to the back right corner, and then I come across the center of the green, and then I make another pass across the front of the green. So I cover 9 areas on the green taking these measurements, and that gives me an average value. And notice what I wrote in here. I said the 4th green is surrounded by pine trees, has partial shade, and sits in a hollow that restricts air movement. The 11th green is at the top of a hill, is in full sun, and has unrestricted air movement. So I measured 2 different greens. One of them, the 4th, has partial shade, less air movement. The 11th has full sun and lots of air movement up there. And then what I did, I looked up the data for, I looked up all of the data necessary to calculate the hourly Penman-Monteith evapotranspiration. And I'm curious, if you use evapotranspiration data to get an idea of how much water the grass is using, or to get an idea of how much irrigation you may want to apply, I'm curious about this. Do you see those data, or do you get those data in an hourly format, or do you get them in a daily format, or do you get them in a different type of format? Because you can express evapotranspiration as an annual total. You could express it as a monthly total. You could express it as a weekly total, or you can express it as daily totals. It's customary to consider daily totals of evapotranspiration because we usually would resupply that irrigation once per day. We would resupply the water loss once, or we may take the evapotranspiration for 2 or 3 days and add that together and then resupply that amount of water. And I'm looking at it here in the chart that I'm showing on the screen, in the chart that you can find if you go to my blog post. I'm showing hourly evapotranspiration, and I wonder if the software that you use or the way that you look at evapotranspiration, if you've ever looked at hourly evapotranspiration before. Anyway, I will be interested to hear. Leave me a note in the comments or send me a message and let me know how you, if you look at it hourly or if you never have before. Anyway, so I calculated this hourly and I then plotted it on the chart. And so there's obviously less evapotranspiration on an hourly basis right around sunrise and sunset. The sunrise was at 5:18 in the morning on June 9th at this location, and the sunset was at 7:28 in the evening. There was a high temperature of 28.6 degrees Celsius at 2:28 p.m. That is 83.5 degrees Fahrenheit. The low temperature was 17.7 Celsius or 63.9 degrees Fahrenheit. That happened at 4:45 in the morning. And I used the data from the JMA Fukuoka station, which is not terribly far from the golf course, but it's not exactly at the golf course, but this is where I can get the data from that is complete enough for me to calculate the Penman-Monteith equation on an hourly basis. And so I got those data, calculated this, and so now I know for each time of the day, for each hour of the day, how much the evapotranspiration was, and it adds together over the course of the day to be 4.1 millimeters or 0.16 inches. Now that's not a huge amount for early June because the days are pretty long, but it wasn't a terribly windy day. And the main thing was it was partly cloudy in the morning, and in the middle of the day it was from 80% to 100% sunshine, and then it was a little bit cloudy towards the end of the day also. So because of that, that little bit of cloud cover in the morning and a little bit around the middle of the day and end of the day also, that cuts the ET down from what it would have been on a purely sunny day. It cuts it down just a little bit. So that was the reference evapotranspiration. So I looked that up. And then, of course, this was a professional golf tournament. And, during a professional golf tournament, you can't really be out on the course and do very much. So I went to the famous Natty Dread Jerk Chicken restaurant. Although in this case, I ordered a hamburger, a delicious hamburger and onion rings. Ate that right in front of the ocean at Natty Dread because the course was completely full of professional golfers out there competing. And then after lunch, I went back to the golf course and I took those measurements again. I'm showing a picture now of when I was at the 4th green in the afternoon. And the 4th green, I measured in the afternoon I was there at, let's see, the second measurement, 12:4, no. Oh, I made a typo in my chart. Oh my goodness. I was at that green at 13:13, and I'm going to have to update that chart. So this picture was taken at just about 1 p.m. and there is light cloud cover. You can see in the photo that I'm showing, there is some blue sky, but there is this wispy white clouds, not thick cloud cover, but there are some clouds, and that will restrict the radiation that reaches the leaf, and then the transpiration will be less, and the ET goes down a little bit. So anyway, that's all accounted for in the reference evapotranspiration measurement. But remember, the reference evapotranspiration, which I've calculated hourly, that is just, it's the output of an equation. But when I measure the difference in soil water content from morning to afternoon, that tells me what really happened. That tells me how much the soil water content has changed. So the chart that I'm going to have to update, and maybe by the time you see this, well, if you're watching this on YouTube, it's going to stay like this forever. But if you go to the blog post and check it out, you'll see that eventually I'm going to get this updated. I just mislabeled the measurement on the 4th green as being from the 11th green. So it's showing that I measured in the morning 17.6% volumetric water content with the TDR 350. I measured the 4th green was 17.6%. And when I went back just after 1 p.m. at 13:13, I made a measurement of 16.1%. So the soil water content on the 4th green went down by 1.5%. And that was, and I know the times because I'd measured 17.6% at 6:43 in the morning, and then at 1:13 in the afternoon, I measured 16.1%. So it's gone down by 1.5% over that time period. And as you know, if we use the metric system, and I leave it to you if you want to do this in inches, but I'm just going to do it the easy way in metric. So I'm going to assume that the measurement that I made of the soil water content with the TDR 350 is consistent down to a depth of 10 centimeters. And then I'm just going to let that be a soil volume of 100 liters, which is what you get when you have 1 square meter down to a 10 centimeter depth. And now 1 millimeter of water applied to the surface is a 1% change in the soil water content, and 1 millimeter of water loss through evapotranspiration is going to be a 1% change in the soil water content. So you can instantly flip between millimeters of depth at the surface, millimeters of precipitation, or millimeters of evapotranspiration, and the soil water content percentage, the VWC. On the 11th green, it started off at a much higher level in the morning. It was at 23.4%, and that went down by 2% to 21.4% when I made the afternoon measurement. But this is not like a measurement prior to the sun coming up and after the sun going down. This is a midday measurement. So that's why I had to use the hourly data. I needed to look at the hourly data, see what the reference ET was for each hour of the day. And then from that, I can calculate my crop coefficient for those greens. And the way that I did that, I showed in the post, I said, because I know the VWC at known times of the day, and because I calculated the hourly reference evapotranspiration on the same day, I can get an estimate of what the crop coefficient is. The crop coefficient is abbreviated capital K and a subscript C for crop. I can get an estimate of what the KC or crop coefficient is for those 2 greens at Kea Golf Club. The accumulated reference ET from the morning measurement time to the afternoon measurement time was 2.3 millimeters. So if the crop coefficient were 1, then I would expect the soil water content to go down by 2.3%. That's how easy it is when you work with metric and make a few reasonable assumptions. If we expect the ET, the accumulated ET from the morning measurement time to the afternoon measurement time was 2.3 millimeters because I've calculated this hourly. So if it's 2.3 millimeters expected, then we would expect the soil water content to go down by 2.3 millimeters because that's how much water would have been evapotranspirated or transpired for a more proper terminology. However, For warm season turf, we often can get away with irrigation at somewhere around 0.6, 0.7 crop coefficient. We wouldn't really use a 100% or a crop coefficient of 1 for warm season turf. So I expected it to be something like 0.6 or 0.7. So for these two greens, what did I actually get? Well, I showed in the post the VWC went down on the fourth green by 1.49%. So that's an apparent crop coefficient for the fourth green of 1.49 divided by 2.3. Remember, 2.3 is the expected change. 1.49 is the actual change. And look at that. It's 0.64. It used 64% of the water that the reference evapotranspiration was predicting. But that's pretty much what I would expect for a warm season grass that's in partial shade. Remember, the reference evapotranspiration is calculated assuming full sunshine. So it doesn't surprise me that in the green that's going to have partial shade for some of that morning, that we would be down a little bit low. And then on the 11th green, which is in full sun and has more air movement, the VWC went down from the morning to the afternoon measurement by 1.95%. So that's a water loss of 1.95 millimeters. And the apparent on-course crop coefficient is 1.95, which is the actual amount it went down, divided by 2.3, which is the amount that it was expected to go down based on the reference evapotranspiration. And that gives us a number of 0.84. So the crop coefficient for that 11th green that day was 0.84. And we can't extrapolate very far. We can't extrapolate very far from just taking two measurements that were made over a 6.5 hour period. But the point that I'm trying to make here is, isn't it really cool that we can do this? Isn't it really cool to be able to make use of the soil water content measurements that a lot of you will already have to see if your soil water content goes down from 18% in the morning to 14% in the afternoon, and if your ET over the course of the day was 4 millimeters, well, then that would be about exactly how you would expect it to go down. That would be a crop coefficient of 1. But probably your crop coefficient is going to be a little bit lower than that. But if you're, and I don't want to say too much more about how your crop coefficient will be, because I would encourage you to try to figure this out. And what I think is so cool about being able to do this is we can start by just doing a few greens, but then you do that, measure a few greens, the shaded greens, the sunny areas, maybe do this in the fairway also. You can do this in the fairway and see how the fairway turf is using water also. And once you do this, and have 10, 20, 30 measurements, which you would quickly get if you measure 5 areas on the property and record those 5 areas today, and then you repeat that for a week, you now have 5 times 7, that's 35 measurements. I think by now it would be pretty clear. Once you get up around 25, 30, 40 measurements, which may take about a week to accomplish, you will now have your minimum and maximum and average crop coefficients for different areas across the property, which is a way to be a little bit more refined in the understanding about how much water the grass may be using. And when you understand how much water the grass may be using, then it's easier to supply that in advance of the grass using it, or it's easier to know exactly how much you would want to replace after the grass has already used it. So I find this really, really useful. And it's actually way, way easier to do this with in-ground sensors because you don't have to spend any time going out and collecting the measurements. You already have them. And I am always surprised at how uncommon it is for in-ground sensors to be used and to put to their full use. I'm sure, I don't know, I haven't seen this in the software of any output from soil moisture sensors. So if you're from one of the companies that makes or sells soil moisture sensors and you guys are already calculating or estimating some site-specific crop coefficients, let me know that I've underestimated the progress of technology. But I think for turfgrass managers, it's fun to make use of the numbers like this. So I will encourage you to do that if you haven't already. And if you can't figure out how to do this, have a look at the blog post, read the blog post again. There will be a direct link to the blog post in the show notes. And I expect that you will soon be able to figure this out. All right, everybody. I will sign off now. Thank you so much for listening. Thank you so much if you're watching this. And be sure to share it with your friends if you think that they might find this type of information useful and helpful, or maybe it's just educational and fun to learn a little bit more about turfgrass. Signing off now for ATC from Yantakao, Thailand. I am Michael Woods. Bye-bye.